radioactivity decay equations. Let's take a look at the radioactive sample. Say, for example, there are N atoms which are radioactive in this sample, and the rate of decay is directly proportional to the number of radioactive nuclei. And this rate of radioactive decay is described by using the term activity. And activity is defined as the number of decay per second, or with the unit becquerel. Hence, becquerel is an average of one disintegration of a radioactive nuclei per second. Hence, activity, or the rate of disintegration, is directly proportional to the number of radioactive nuclei. Activity is equal to the change in the number of disintegration over a time span of delta T. Change in N is always negative as the total number of radioactive nuclei is decreasing. Hence, we place a negative sign. Those who have learned chemistry, you will know that this is very similar to the first order reaction that you have learned in the topic called kinetics. And hence, using A equal to minus dN dt and replacing A as minus dN dt equal to lambda n, we'll be able to integrate and derive an expression for the number of radioactive nuclei over time. So N is equal to N naught epsilon minus lambda T. Let's now explain the symbol. N naught is the initial number of radioactive nuclei when time is 0. Lambda is the decay constant, and the unit is in per second or per year. It can also be in per minute or per hour. And lambda is the proportionality constant between activity and the number of radioactive nuclei. Hence, in this topic, the total of 3 sets of formula that you need to know. The first set is A is equal to lambda n. A is, and I recap, A is activity, and n could actually be calculated by using mass of the element, of the radioactive element, divided by the relative atomic mass, or the mass number of the element, and multiply by Avogadro's constant. And the third formula that you have is n equal to n naught E minus lambda T. And bear in mind that n can also be replaced with activity, or replaced with the mass of radioactive atom, or C, where C is the count rate, and the count rate is determined by a radioactive sensor that tracks the number of disintegration or the decay rate. And hence, in the third formula, we'll use S to possibly represent N, which is the number of radioactive nuclei, A, which is the activity, M, the mass of the radioactive nuclei, or the count rate displayed by a radioactive sensor. X equal to X naught E minus lambda T. And if you were to ln on both sides, then ln X is equal to ln X naught minus lambda T. This formula is given in the data booklet. This is what you can derive from that formula. And this formula is useful if you want to plot a straight line graph, specifically plotting ln X versus T, where lambda is your gradient. Half-life of a radioactive nuclei is the average time taken for its activity to fall to half its initial value. Mathematically, that could be derived. Given a radioactive sample of N naught, the time it takes for it to drop to N naught over 2 is your T half. So using the formula where N is now equal to N naught over 2, that is equal now to N naught E to the power of lambda T half. So hence from this expression, E lambda T half is now equal to 2. So if we were to ln on both sides, we will be able to end up with this expression. And this formula is inside your data booklet, and you will use this formula to relate half-life to decay constant or vice versa. And that also explains why the unit of your decay constant is in per second, per hour, per minute, or per year. Let's now take a look at some of the graphs. The first graph we're going to look at is your count rate versus time. And in this case, if we start with x naught, the time it takes from x naught to go to x naught over 2 will actually be the first T half. That's your first half-life. And from half x naught to a quarter x naught, which is from here to here, you get another T half, and you can see that the the half-life is constant, and so on and so forth. We can also picture it in terms of the mass of the radioactive nuclei. Say, for example, we start with 10 grams, and the time it takes for it to drop to 5 grams would actually be the first half-life. And for 5 grams to drop to 2.5 grams, it will require 2 half-life. And for it to drop to 1.25 grams, it will require 3 half-lives. This next graph itself looks at the percentage of atoms remaining, which means the number of, you're plotting the number of radioactive nuclei over time. We wanted to sketch a graph to clearly depict that as the half-life increases, the line tends to actually straighten. And clearly in this case, the radioactive nuclei that contribute to the blue line has a half-life of 50 years. And conversely, if you look at the light blue line, it is 300 years. The next graph we want to factor in background radiation. So what is background radiation? Background radiation comes from mainly 2 sources. The first source in any of the radioactive elements found in rock, soil, water, air, or even in our food. All these radioactive elements give rise to low-level radiation, which may not directly harm us, but still contributes to the count rate. The other second source comes from cosmic rays from space, where the radiations can penetrate through our protective atmosphere as well as our magnetic field. So how background radiation affects our analysis of half-life is as follows. We now take a look at the red line, where the count rate includes the radioactive nuclei as well as your background radiation. If you take the count rate as a becquerel of 120, then 60 is here, and you will estimate that to be your first half-life, which is about 400. And from 60 to 30, we will now be able to look at our second half-life, which will now clearly goes to a value of about 950. So what this example illustrates is that when you look at the half-life of a radioactive substance and the half-life is no longer constant, we need to bear in mind that it means the count rate is no longer just quantifying the number of disintegrations of the radioactive nuclei. It would be including background radiation that contributes from low-level radiation of radioactive elements on Earth and as well as cosmic rays. And if you know that the background count is approximately about 20, and we can determine that by moving the radioactive source away from the sensors, and if we still register a background count of 20, then we could now subtract all the readings that we have recorded by 20. So 120 will become 100, and so on and so forth. So from subtracting by 20, we will now get the blue dotted line, which only quantifies the count rate of the radioactive substance. And from there, if we take a look at the half-life, we will now note that the half-life has become constant, and in fact, the half-life is 300 years. The next graph displays the percentage of radioactive parent and non-radioactive daughter nuclei. So say, for example, we have the radioactive parent, which is X, and after disintegration, it will become Y. We need to assume that Y is no longer radioactive, which means it won't further disintegrate or break down. It won't further disintegrate. Let's start off to use a pie chart to represent the number of parent nuclei. And after one half-life, half of X is converted to Y, which is actually your daughter nuclei. And so the number of daughter nuclei that you have will be 50%. The number of daughter nuclei that you have will now increase from 0 to actually 50%. Let's take a look at what happened after another one half-life. After the second half-life, you will find that only a quarter of your parent nuclei remains, which is Y is 25%, while 3/4 of your nuclei is actually Y, which is your daughter nuclei, and so on and so forth. At any point, it is important to note that the number of parent nuclei, when summed up with the number of daughter nuclei, must still give 100%. The green line will depict the percentage of parent and daughter nuclei, which will be 100%. In the next graph, we are looking similarly at the same thing. We're looking at the radioactive parent nuclei, which in this case is your CE, and it disintegrates to form your PR, which in this case is the daughter nuclei, but the key things to note the difference with the earlier example is that it's now radioactive. So let us take a look at the graph of the parent nuclei first. The parent nuclei graph is demarcated now by the red line, which is actually no different from the earlier example. So as far as the parent nuclei is concerned, we will keep undergoing this integration. Let us now take a look at the radioactive daughter nuclei. That would have been different because it will no longer just be increasing, because as it increases, its total number of radioactive daughter nuclei increases. It will also means that they would undergo further disintegration. They will also behave like parent nuclei, where they will disintegrate, and hence because of that, you will find that the activity recorded is such that initially the mass of the daughter nuclei increases, but subsequently, as the rate of disintegration of the daughter nuclei, the activity contributed by PR will start decreasing as the mass of the daughter nuclei decreases. Meaning to say that this is, at this point here, this is when you get peak mass of PR during the period of its disintegration. And finally, it is important to note that the total activity recorded, which means in this case, if you use a radioactive sensor, then the count rate registered will be equal to the count rate of CE, which is the parent nuclei, plus the count rate of your PR, which is your daughter nuclei. So summing that up, this is how the graph will look like, depicted by the green line. To understand how the green line relates to the blue and the red is when at any point of time, if at any point of time t, if you sum this value with this value, you will end up with the total activity represented by the green line. And that is the reason why as time increases and pass by, the green line would in fact coincide with the blue line since most of the parent nuclei have been disintegrated. The final graph we look at stems from the formula n equal to n naught E minus lambda t. If you ln on both sides, this will end up to be the expression, but more important of all, if you were to plot ln n versus time t, then the gradient is minus lambda, and the y-intercept is actually your ln n naught. Let's now take a look at the ln n graph of 3 radioactive nuclei. Specifically, the 3 radioactive nuclei is your iron, Fe, your manganese, Mn, and your CO, cobalt. Each of them is depicted by a line. In the case of iron, let's represent it with a brown line. In the case of your manganese, it is actually the purple line, and the cobalt is the blue line. The combined activity of all the 3 nuclei is now represented by actually the green line. And again, in order to obtain the total activity at any point t, we just need to sum up the activity contributed by your cobalt with the activity contributed by iron and the activity contributed by your manganese. By comparing the 3 straight lines, we know that the iron has the highest gradient. Because its gradient is the highest, and since gradient is equal to minus lambda, we therefore know that the rate constant for iron is the highest, while in the case of your cobalt, it is the lowest. And using the formula whereby lambda is equal to 0.693, which is in fact ln 2 over T half, we could now conclude to say that since lambda is the highest for iron, iron will now have the lowest half-life, since the half-life is inversely proportional to the decay constant. And from here, we can also argue to say that the cobalt, which has the lowest decay constant, it means that cobalt's half-life will be the highest. And finally, it's important to note that why in the combined activity graph, it will eventually becomes a straight line. It is because it is when, and that occurs when the combined activity is the activity contributed by the radioactive nuclei, which has the highest half-life. As observed down here, manganese and iron has the shortest half-life. Therefore, after approximately about 1,700 days, manganese and iron no longer contribute to the combined activity, which explains why beyond 2,000 days, the graph of the combined activity will coincide with that of cobalt, since cobalt is the only radioactive nuclei that contributes to the combined activity since it has the highest half-life.